Hi, this is Danielle, and this is my final project for the Forest Ecology Unit.
Remote sensing, which is the scanning of the Earth by a satellite to obtain information about the surface, can be used to investigate shifting cultivation in Thailand. I'll begin by offering a crash course on the science behind satellite imagery. There's a constellation of satellites in our atmosphere that are circling the Earth in every direction. Today we'll be looking at a certain type of orbit called a sun-synchronous orbit, where the satellite travels over the polar regions. It moves synchronously with the sun, which means it's always in the same position relative to the sun. That means that the satellite visits the same spot on the Earth at the same local time each day. For example, it would pass over Chiang Mai at noon every time. This helps a researcher always observe the same point on Earth under the same conditions. As the seasons change throughout the year, the orbit of the satellite adjusts to maximize the number of hours it gets in the sun. Every object is constantly emitting energetic radiation in proportion to its temperature. However, we can only see visible waves between 400 and 700 nanometers long. The sun is responsible for emitting these visible waves, as well as UV rays and near-infrared rays. Different surfaces on the Earth reflect different waves depending on their properties. For example, an apple would reflect mostly red waves. All these types of reflected waves are absorbed by satellites in the atmosphere. The Earth is emitting its own waves as well, but these aren't confused with the sun rays because they're thermal infrared. After satellites absorb all these waves, researchers can determine what the different types of land are based on what types of wavelengths they reflected. For example, since trees reflect mostly near-infrared waves, you can determine that an area with high NIR is probably a forest. Now we'll shift to how these satellite images are used. Through aerial imagery, it's possible to assess how degraded a forest is. One indicator is canopy cover loss. For example, a decrease in canopy cover could be attributed to logging. Secondary indicators are signs that the forest may be degraded beneath the surface, that is, under the canopy. For example, a road that bisects a forest may cause habitat fragmentation. You can also use images to measure other forest parameters, like biomass. Active remote sensing, like radar or LiDAR, emit waves from the satellite. When the waves bounce back, the satellite can calculate how far away that object is. To process a satellite image, the first step is often to categorize the land type based on its ecosystem and use. This process is completed with coding software and also comparing the land type to actual field data. The goal is for the classification to be as accurate as possible. Accurate classification can help determine the total area that's forested and the total area cultivated. It can help inform models of carbon sequestration, and it can track local and worldwide trends in land use changes. Now let's put this in a Thai context. Remote sensing can be used to calculate how much land is involved in shifting cultivation, and can even be used to estimate the change in the duration of fallow periods over time, or answer other local research questions. It is challenging to delineate shifting cultivation use because of the dynamic properties of the land. Mixes of man-made and natural land uses are missed in traditional classifications. For example, shifting cultivation lies somewhere between forest and agricultural fields. So how can we tell apart forest versus fallow? Well, I took a look at some literature to see what scientists are doing right now. Solution number 1 is to create a time series analysis. While a single image of land under shifting cultivation might resemble either forest or field, a series of photographs taken over consecutive years can be stacked together. The resulting composite image has a distinctive spectral signature that can be distinguished from other land types. One worldwide study looked at shifting cultivation across the globe using a stack of 14 Landsat images at 30-meter resolution. The Landsat mission has had satellites in operation since 1972. This study used visual interpretation instead of an automated approach to discern the characteristic shifting cultivation pattern. Ultimately, it achieved 88% accuracy. In Asia, they estimated a loss in area under shifting cultivation in the next few decades due to rapid economic development, and predicts this decline may raise the issue of livelihood security for farmers. Another study analyzed boom crops in Southeast Asia, including a case study in the northern Thai highlands. It also used stacks of Landsat images, which it supplemented with field interviews and photographs, Google Earth images, and agricultural land concession data. Since the data was so detailed, it was possible to distinguish between certain tree crops based on the timing of their growing seasons. However, since the process was not automatic, it was time-consuming, and collecting large numbers of classification training and verification points may not be able to be upscaled. This next research tried to reduce the amount of data necessary by using just 2 images to determine whether shifting cultivation was occurring. One photo was taken right after harvest in November, and the other was right after burning in April. Overall, they achieved 80% accuracy. Next, they calculated the average duration of the fallow period between crop cycles in the region. This simple calculation used just 2 variables derived from the photos. One was the number of consecutive years of planting, and the other was the area ratio of fallow to active fields. However, this only works if you can identify the entire area being managed. This calculation for Meghalaya, India, found a regional average of only 2.4 years fallow. A slightly different approach is to distinguish shifting cultivation cover class using texture measures in object-oriented classification. Let me break that down. Measuring textures is like measuring the extent of variation between neighboring pixels in an image. Using this technique, mature forests and regrowing secondary forests appear very different. This technique helped land cover classification accuracy double, especially in areas with a long fallow period. To delineate the boundaries in shifting cultivation landscapes, multiple cover class ratios need to be used, such as the ratio of young forest area to grassland area. Another advantage of this method is that it only requires 1 image taken at one time. One problem you often run into in Southeast Asia is the lack of constants. There's both great variety of natural types of forests and also seasonality of the vegetation, which both create high variability in the strength of reflectance. I'll conclude by talking about just one more application to Thailand. Shifting cultivation is largely blamed for deforestation. By tracking land use change, it is possible to demonstrate what happens to forests that are no longer farmed. Some research shows that land in Southeast Asia previously under shifting cultivation is widely being converted to commercial rubber tree and oil palm plantations, which cause greater environmental degradation. Better research on land use can create more productive conversations on the future of shifting cultivation in northern Thailand. Thanks so much for watching this presentation. and just let me know if you have any questions or want to talk to me more about remote sensing and shifting cultivation in Thailand.